Hello, everybody. Welcome to our ProGeek Screen Tech Live today. It's my great pleasure to welcome again Mr. Carl Welty, architect and also a visionary in terms of sustainable architecture, here with us on another session. Today, we are going to talk about retrofits. Now, for those of you that are working with sustainability, working with architecture, building or construction, you know, retrofits is a massive, massive topic, huge demand, a lot of potential. And there are many different factors to retrofitting buildings, right? Many elements, whether we talk about water, about maybe also other elements of efficiencies that you can achieve with retrofits. We will be talking today about retrofits for energy efficiency, and how to kind of have thermal comfort in the building, using most of all low-tech solutions, energy efficient solutions that are not increasing the demand of the building itself. So this would be a little bit like an intro on the topic today. And I'm happy to share with you a little background information on Carl and his work. So let me just share this one with you so you know who you are listening to today. So Carl is in his current role leading the team of Carl Welty Architects based in California. He brings over a decade of expertise in general architectural services, coupled with profound specialization in energy efficient design and resilient construction. Throughout his journey, Carl has been advocating for nature-based solutions and passive solar-oriented designs, resulting in buildings that excel in performance while nurturing the environment. Carl has been exploring alternative construction technologies, aiming for creation of structures that not only endure but thrive over time. With a legacy that spans over various ventures, including his role as the principal at Claremont Environmental Design Group, as well as in the capacity as the Director of Architecture and Planning at the Benning Land Trust, his visionary leadership continues to shape the sustainable architectural landscape. So with this, let me welcome Carl today here with us.
Good afternoon for you guys, and good morning for me. It's great to be with you. Always a pleasure to join your conversations.
Absolutely a pleasure also to have you here. We are going to do a little brief on the basics of the topic, some kind of information sharing for you to kind of take notes, learn, observe. If you have any comments, we are more than happy to kind of receive them. We have a stream running on Facebook, LinkedIn, and YouTube. So wherever you are, let us know what you think about this concept. If you have questions, also a great opportunity to reach out to Carl and kind of get his feedback on the points which are of interest for you. So with this, let us maybe go into the brief, Carl. Do you think it's a good time for that? And then we have Q&A.
Much to cover. So yes, anytime.
Let's go.
Okay. Thank you very much. Carl Welty, an architect in California. I like to say that I am old enough to have gone to school in the late 70s and early 80s, where we were introduced to what's called passive solar design, which these principles continue to produce buildings that are twice as efficient as common high-tech solutions. So the environment. So why retrofitting to buildings, particularly to reduce the impact of air conditioning? So today, air conditioning accounts for about 10% of global electricity consumption. Energy for air conditioning is about 8% of global greenhouse gas emissions. Leaking refrigerants adds another additional 8% of global greenhouse emissions. And by 2050, because of warming climate, the energy demands for air conditioning is expected to increase by 6 times. So cooling buildings with little or no energy is extremely important. Introduction to passive solar. I'm going to do a quick introduction to passive solar. Unfortunately, little understood, but these principles have been around for a long time. So introduction of passive solar to both provide heating and cooling. Socrates understood this 2,400 years ago, that the same principles continue to incorporate into buildings today, resulting in the most energy efficient buildings. Passive solar, the facts of nature. It's so very simple, but sometimes our culture, we don't do simple very well. But the sun rises in the east and sets in the west. The sun is lower in the winter and higher in the summer. In Mediterranean climates like California and high desert climates, the regions have within the regions that have low humidity, the summer nighttime temperatures are 25 to 30 degrees cooler than daytime temperatures. And this is what you can rely on to cool your buildings naturally. In humid climates, it makes it harder to cool buildings. Happy to discuss this in more another time. But so design principles: orient building to the south. This makes it easier to maximize heat gain in the winter and minimize heat gain in the summer. The use of roof overhang or vegetation to shade south-facing glass to minimize summer heat gain. Minimize windows on the east and west-facing walls. Design the building to maximize natural ventilation to cool the building at night, and incorporate thermal mass in the building envelope, typically concrete or water bodies. Performance results. Incorporating these principles continue to produce buildings that are 50 to 80% more efficient than normal baseline buildings without increasing construction cost, reduce energy costs for the life of the building, eliminate the need and reduce the need for cost to replace equipment. And these design strategies connect the building and users to nature more holistically. I want to discuss a really critical part of this that seems to confuse people. The building envelope requires two parts. There's the insulation that helps keep heat in or out, and thermal mass, often concrete, some sort of substance that absorbs heat and stores it like a battery. A concrete slab or concrete. Oftentimes people think of thermal mass as the same as insulation, but it's very different and it functions very different. For example, a concrete wall has very little insulation value. So the California minimal standard for an exterior wall, which is 6 inches wide, would need to be 95 inches thick in concrete to provide the same insulation value. So concrete's good for thermal mass to store heat, but it does not keep heat inside the building once it's. So nature-based zero energy air conditioning, summer nighttime passive cooling, relies on the temperature of space is minus 455 degrees Fahrenheit. The space's cold temperature extracts heat from the earth, buildings and air climates and dry climates. In California and Mediterranean climates, the nighttime temperature is much colder than daytime temperature. So even if it's 100 degrees Fahrenheit, it's often 70 degrees cooler at night, and you can rely on this differential to cool a building naturally. I know from California that these principles could be incorporated and eliminate the need for air conditioning within 30 to 40 miles of the coast. The same is true for Mediterranean climate and any parts of the globe that nighttime temperatures are cooler than daytime temperatures. Retrofitting existing buildings. So incorporating these passive solar principles in existing buildings for cooling is pretty easy because you're not dependent upon solar orientation for cooling. Existing buildings can be retrofitted for passive cooling regardless of the solar orientation. I'm motivated by this question, and common wisdom in my green design world in California is that existing concrete buildings are expensive and complicated to make more energy efficient. And also 80%, most of the buildings built in California before 1985 are uninsulated concrete buildings. So why focus on existing buildings? I like to think that the greenest buildings are the buildings not built. So if we can retrofit existing buildings to be more energy efficient, it's a really net benefit. So concrete as thermal mass. So I hope it helps understand. So concrete in a passive solar building absorbs heat in the daytime and keeps the space warm at night. And in the summer, the heat is absorbed because it's warm, and it's vacated or radiated out into the night at nighttime. So the process of retrofitting buildings, again, I think can be very simple. Insulate the outside of the building, turning the high massive concrete or stone walls in beautiful European older buildings, turns this thermal mass that's a liability into an asset. Looking at cost in California, the cost of insulating an existing concrete building is about 80% of the cost of a high-performing heating and cooling system, which if you pursue that route, you're going to still spend $1,000 a month for energy, even for an efficient system. But once insulated and retrofitted, the monthly energy cost will be zero or near zero within 30 to 40 miles of the coast. We can insulate these concrete buildings with available materials, metal panels, metal insulated panels, or other easily available building materials. A good R value, we call R value in California, is 7 to 8 an R value of 7 to 8 per inch. So these can be applied to the outside of walls very easily without increasing the weight and strain on the building. Other architectural features: light scoops designed to vent buildings at night, wind cooling tower elements over existing stairs in high-rise buildings, wind catchers, common throughout Middle East and Asia, and windows to optimize cross ventilation and nighttime passive cooling. So these are the toolkits that one needs to retrofit a building. Some lessons from ancient history. There's artwork in the Egyptian buildings that show wind catchers and wind ventilation systems that are been around forever. One of my favorites are wind cooling towers from ancient Persia. Historically, we know they've been building these for a couple thousand years. The oldest existing towers are 600 to 800 years old and have continued to cool those buildings for 600 years, 800 years with no maintenance and no recharging of energy. Wind catchers and some big ideas of using wind cooling towers and bringing air from the ground. I invite anybody who is interested to just Google Persian wind cooling towers. They're very sort of kind of amazing strategies. Wind catchers from Hyderabad, India. So just to rehash. So insulate the building, wrap the building with some insulation system, systems for ventilating the building at night, and incorporating features to reduce summer heat gain, overhangs, or vegetation. This is a very, very common building in Southern California, in most of the world, in older industrial areas. In the 20th century, if it's a 18th century building, it's a stone building, but the same principles apply. So this is a case study that I'm working on. So very typical building. 90% of old commercial buildings in California and the rest of America look like this. So to start with, you develop landscape to shade the building from the south and the east or west, which gives you an opportunity to create outdoor spaces for employees. The simple building can be wrapped in multicolored metal panels to renew the aesthetics of the building. Incorporate scoops and lights, wind scoops and light scoops on the roof for nighttime cooling. If needed, incorporate shading devices for south-facing sun to keep the summer sun out of the glass and let the winter sun in. This is easy to do because, as we know that the winter sun is lower in the winter, and so a simple roof overhang will shade the glass in the summer, but let the winter sun in for heating. Some benefits of retrofitting existing buildings: we can eliminate the need for energy for cooling for the life of the building. Little to zero maintenance or replacement costs. HVAC systems are typically replaced every 20 to 25 years. So once retrofitted, a building is going to provide thermal comfort for the life of the building. We hope 100 years. Retrofitted buildings will provide thermal comfort during power shortages or rolling brownouts. And retrofitted church, synagogues, and mosques can become cooling centers during heat waves. This is a building that inspires me. It was a synagogue designed by my old professor from California. The building is in a relatively warm part of California, but built without an air conditioning system. So this building, unfortunately, is the rare building, but Ken Haggard designed this building without an air conditioning system, and he's shown that it's kept cooler than a building with air conditioning. So this building, for a very long time, will have no cost to replace the air conditioning system, and there's no refrigerant leakings. So it's clearly a better option than using high technology. This is another example. Right before COVID, the synagogue that my family belongs to was talking about retrofitting a building built in 1962. Typical of buildings built in 1962. It's on insulated concrete walls. So I presented this idea that you insulate the building and then provide scoops on the top to bring in natural light, and also to bring in natural ventilation at night. This building is close to mountains, and so in addition to the cool air at night, you can also take advantage of a cooling breeze that comes down from mountains. It's kind of a simple diagram. I presented this idea to the synagogue and claimed that it could probably reduce the energy consumption for summer cooling by 50%. Ran it by my professor, Ken Haggard, who's clearly a kind of world leader in this sort of strategy. I was right, except for that he thinks that you could probably reduce the energy by 90%. So this gives me lots of confidence that it is absolutely doable. And that's it. Thank you very much. And available for our questions.
That's beautiful. That's beautiful. It was super insightful. Thank you so much, Carl, for sharing your case studies and also experience in this field. And we have quite some questions over here, so let's go into them. Now, when talking about retrofits and the projects which you introduced to us during the session today, one can notice that we were talking essentially about single or two-story building types of Now, I mean, I'm coming from Slovakia, post-communistic country. You know, we have a lot of multi-story buildings, which are kind of in the line, waiting for renovations, etc. So, what would be the retrofit approach that you would see as feasible for high-rise buildings or for taller buildings of such a structure?
Clearly, a high-rise buildings makes it more difficult, but there's some work being done with in new buildings where they're using a stair tower as a wind cooling tower. So it's possible to retrofit these larger buildings to increase ventilation. But you know, even without doing that, if the building once it's insulated, in a typical Soviet bloc building, you could create ventilation through windows, a window strategy, or other smaller wind scoops to cool the building, the apartment at night,
Mm-hmm.
and that thermal mass will be chilled. But also a lot can be done to keep the heat out with shading devices.
Shading devices. So when we talk about shading, is there anything that you kind of work with or consider in your projects in terms of facades, like some applications on the facade that can aid this purpose to keep?
I would always rely on a roof overhang.
Mhm.
Um, there's in California is becoming more uh, is requiring buildings to use high reflective glass, low E glass, um, which I have many problems with. One is that
Mhm.
um, they keep heat out, but they also they keep heat out in the summer, but they also keep heat out in the winter. Um, they they don't make heat disappear; they just reflects it out, so it increases the heat island effect. And new information coming out is that it doesn't last very long. So even a fabric awning that can be easily replaced every 10 years is a lot, is a viable option for shading.
Mhm. Okay, and I hear you. I definitely hear you. And when we talk about, because also with one of the case studies that you share with us, there was a landscaping element, smartscaping, how we also call it or call it in this area. So, what is your perspective on high-rise buildings again, or even lower structures or lower builds? In terms of greenery, vertical application of greenery, green roofs, green walls. What is your perspective on that? And what are maybe the pros and cons that you kind of would like to highlight?
Well, always looking at history. As an example, um, the the classic courtyard house throughout the world, the Mediterranean, where there's a courtyard with a water feature and vegetation. That combination of vegetation and water elements reduces the ambient temperature in that courtyard by 10 to 15 degrees. There's some other modern projects that sort of show that this is quite doable on a larger scale. Um, to the use of vegetation, my thinking is that whether you're talking about an architectural feature or landscape, one can all one should look at how can I use this element to reduce energy. So shading,
Mm.
and particularly east and west facing windows, which I mentioned. There is really no architect. Well, if you have west facing or east facing windows, shading or landscape is a better option because like a horizontal awning or roof overhang does not keep the low sun out of the building.
Mm.
So landscape can be a critical component to that. Regarding high-rise buildings, there's an opportunity to incorporate a landscape strategy outside, let's say, the doors of the building that can reduce the ambient temperature again by 10 to 15 degrees. So when people go in and out of the building, the air that's going in and out of the building is cooler than the air without the landscape. And so going back to the lessons from ancient history, that a well integrated landscape architecture strategy can reduce the ambient temperature significantly. So in high rise buildings and buildings when there's landscape outside, which is where we put it, there's often a missed opportunity to use that landscape to reduce the ambient temperature.
Mm. Great. I hear what you're saying, and also let us maybe bridge that to another part of our discussion, because when we were talking about retrofits, you mentioned several times. I mean, insulation is quite the thing in this matter, in the approach which you introduced. Also with the respective zoning that I would again maybe reference those that watch the replay or follow us now on the stream, that go back to that as well, that there is a certain zoning or certain location, certain ecotype, certain conditions that is particularly suitable for. So it's not a silver bullet that we say this is suitable for every ecotype or every building, just to put it into perspective. But when we talk about insulation, is there any kind of particularly suitable eco-friendly material that you would kind of highlight or share with us for retrofit?
I can never remember the various different types of insulation, but there's unfortunately, I mean, there's the insulation strategies like hempcrete and other sort of more natural materials. They with the insulation value in America we call R value. In Europe it's it's thermal resistance, but the numbers are sort of the same thing. These more natural materials which we'd want to use, but they don't provide the same R value. The R value, you know, the value per dimension, inch or centimeters, is usually half. So I'm pretty sure if you choose a more modern insulation material that maybe uses a bit more embodied energy, you're probably going to, and I'm actually working on this calculation, but you're probably going to reduce the carbon footprint or the energy consumption over the life of the building more than what you would save using a more natural material. But always hoping for higher quality natural systems, but they're not always there yet.
Very insightful. Thank you so much. And of course, we're more than happy to share any findings from the case studies from running projects with our audience that can leverage that in their projects. And now looking also at the next part of this is when we talk about life cycle assessment. You kind of mentioned it also in the previous answer of yours. How much do you work with life cycle assessments right now for your projects? I mean, is it like a core thing, or is it like a natural step that you do? You have been for a long time in nature-based building or development. So what's the role for you of life cycle assessment?
I think it's enormously important, and another reason why I'm so animate about natural systems or passive buildings, because, as I said, a well-designed passive solar building, I like to think of it as the building shell itself is an energy system. So you need fewer or no cooling systems or mechanical systems. So that building shell that's providing 50 to 80% of the energy required in the building without any replacement cost for 100 years is enormously more efficient than and cost effective than replacing solar panels, batteries, or mechanical systems over the life of the building. And I'm not saying that solar panels don't have their place, but if we can make the building shell that will last 100 years without any maintenance, then you can use fewer solar panels and fewer high-tech solutions that always have a higher carbon footprint and embodied energy and more expensive than just making the building shell absorb energy and manage energy.
I hear you. So this leads us also, talking a lot about energy efficiency materials, LCAs. We come very, very fast to some kind of framework, some kind of, regulation, certification, all this type of stuff. So what's your perspective also on the certification standards that we have, maybe challenges or opportunities within the frameworks that are currently still in open or being set up?
Always a politically sort of challenging question to answer. The strategies, the passive solar, these are natural system strategies. For example, I designed a house in Santa Monica that my clients, Santa Monica is in the coast of California by Los Angeles. My clients have used no energy for heating and cooling. Very easy on the coast. It's a LEED Platinum building, but LEED and other certification systems, they could promote these strategies more. God help me for saying this, but the first step to a passive solar building is orientation. And if people are interested, I have my list of best buildings, and you show me a building that's 80% better than normal, then I'll show you a building that's oriented to the south. There are no exceptions. There's just one can Google this and research this, or they want my list. Happy to share that at another time. But any building on the planet that's 80% more efficient is a building that's oriented to the sun and incorporates these natural systems. So the evidence is just overwhelming. But in LEED only gives you 2 or 3 points for orientation, which to me seems a little it should be more, because just this simple act of oriented building can impact climate change or energy use more than any other design strategy. So some of these certification systems I think should promote these strategies more than they do.
Thank you so much for sharing this. Now, that is like, it's a nice snowball that over the course of our discussion today, when we talk about the little steps that or the dots which we try to connect here on low tech, energy efficient retrofits for providing thermal comfort in buildings, which is resilient and which is also kind of helping manage the changing climate, which we all need to adapt to, and the best possible way. And with this, I would maybe just close with a more generic note or question on that, because there are apparently many projects that you also kind of work on, get inspired to have the opportunity to kind of review as a peer group. What is the most underrated principles that you see are kind of would be helpful for of course the situation, apologies, in which we are in terms of climate change context, but also efficiency, etc. What are the most critical three that this should be actually kind of that we should pay more attention to that?
This is I guess as a somebody from the educated in the 70s and 80s, we use the term passive solar. Maybe a better, more accurate term is natural systems. So natural systems are knowing how the sun moves through the sky, taking advantage of local climate, local building materials. There's just a treasure trove of lessons to be learned. And again, looking at ancient history or ancient architecture, like the wind cooling towers and orientation, like Socrates' house. Socrates talked about this importance of orientation 2,400 years ago, and eventually in his I guess teaching of his students influenced the fact that most Greek cities built after 350 BC, about 500 years after Socrates, are oriented to the south. So again, there's just overwhelming evidence that orientation starts everything, and if you don't get the orientation right, then you're always playing catch up. But once you pay attention to nature and the sun and everything else, energy efficient solutions just kind of happen. So working with nature is always sort of more efficient, more cost effective, more resilient than trying to fix problems or perceived problems with technology that always breaks down, requires more maintenance cost, reuses more resources um, for um, for replacement. Just maybe in closing, like if you a good passive building, and there are examples, high-rise buildings, but the building shell itself is the energy system, and once done, there's just no maintenance, and it's just going to be there for 100 years or more, providing thermal comfort, reducing the energy consumption by 50% or more, without maintenance or replacement costs. So that's
quite some interesting numbers, interesting figures, and insights and perspectives to work with, and especially our favorite topic, building the future that is sustainable, ecological. That's what we like. So with this, thank you so much, Carl Welty from Carl Welty Architects today for the session on retrofits.
I was happy to join you in your your conversations, Jana, and so always a pleasure. Thank you for letting me share these ideas.
More than welcome, and I wish you a great rest of the day. I see you on the next one. We have quite an interesting topic upcoming shortly, which is going to be around green certifications, where I believe we're going to see at the more human hour, maybe Mr. Carl Welty again. And for you, thank you so much for taking the time and being here with us at this hour. For you, Carl. And yeah, see you on the next one. Have a great day.
Okay, thank you. Bye-bye.